Okay, yeah. So alcohols. Next, this is basically our next organic group that we're just going to have a quick look at. So we're going to look at what they are, how we name them, how they bond with hydrogen, and the use of alcohol. And that's just sort of like our first quick sort of intro to alcohols, and we'll do a bit more on them as well today. So as we found out with lots of the other organic compounds, in organic chemistry, alcohols are a homologous series of organic compounds. They have a general formula which you need to learn and you need to know, which is CnH2n plus 1 OH. So it would help if I also underlined the OH as well. And their names end in ol. So functional group in alcohols is the hydroxyl group, which is our OH here. So naming them, so for example, if you've just got one carbon atom, it would be CH3OH, and then it's just all on the end of the beginnings that we would normally use. So methanol, ethanol, propanol, butanol, pentanol, and hexanol. So that's the basics of naming an alcohol. But actually, as we've discussed before, we actually look at where this functional group is, where this hydroxyl group is, and that adds to our naming. So if an alcohol has 3 or more carbon atoms, they're able to display positional isomerism. Obviously, we've talked about what isomerism is before. We've got the same molecular makeup, but we've got a different display formula. So in positional isomers, the number of a carbon to which the hydroxyl group is attached is written before the ol. So for example, propan 1-ol here, and then propan 2-ol in this situation. The presence of the hydroxyl group is really important because that actually, because this hydroxyl group, it has electronegative oxygen atom attached to it. So as we can see here, so the OH itself, the hydroxyl group itself is polar, which makes our alcohols polar. And because the alcohol, because of this OH group being present and we have an electronegative oxygen atom in it, it makes the whole alcohol polar. And then that means that alcohols can take part in hydrogen bonding. And generally what happens is hydrogen bonding between alcohol molecules. So it's in between, so intramolecular, so in between the two. So hydrogen bonding between alcohol molecules means that an alcohol's boiling point is a lot higher than that of an alkane that would have a similar molecular mass. So if we compared methanol, which has a molecular mass of 32, and ethane, which obviously is an alkane, which has a molecular mass of 30, very similar molecular masses. Methanol boils at 64.7 degrees Celsius, but ethane boils at minus 88.6 degrees Celsius. And that's that presence of those hydrogen bonds. They increase the strength, it increases that bonding, which makes them harder to break, which makes their boiling point a lot higher. Alcohols can mix with water because their molecules can form hydrogen bonds with water molecules as well. So that's really important to know. So alcohols can actually mix with water. So alcohols, making wine and cider. Alcohol has been produced by fermentation of sugars for thousands of years. And we get sugars from fruits or grains such as wheat and barley, and we mix them with yeast and water. And when this happens, we produce ethanol and other compounds. Industrially, sugarcane or molasses, which is a product of refining sugarcane or starch from potatoes and corn, can be used for fermentation. The product is actually a mixture of water and about 15% ethanol by volume. We don't produce any more alcohol than this because the yeast is denatured by the alcohol, so it stops being able to ferment, and so then no more alcohol could be produced. We can then use distillation to remove that water from the ethanol, so then we can have pure ethanol. So how do we make ethanol from ethene? So we can actually make ethanol from ethene. So industrially, we can hydrate ethene to form ethanol. So for here, we've got our ethene, we've got water, and we produce ethanol. So let's have a quick look at this. So when we're doing this production of ethanol. We carry these reactions out under compromised conditions, and that is a small excess of ethene at a temperature of 570 Kelvin, a pressure of around 6 to 7 millipascals, so 60, 70 atmosphere, and the reaction is catalyzed by phosphoric acid. So it's really important to remember that phosphoric acid here. So what actually happens? Well, our phosphoric acid is a polar molecule. So if we have a look here, we've got our our ethene and our phosphoric acid. And phosphoric acid is polar molecule. And you can see that here it's polar in very similar way to how our alcohols are. We've got that electronegative oxygen atom. So we have that electron density in our double bond here in ethene. So this is going to be very similar to when we've talked about alkenes before, in the double bond in ethene. And what this electron density in our ethene can do is it's able to attack that slightly positive charge on one of the hydrogen atoms. And it's that hydrogen atom that has a positive charge that's attached to the oxygen. And basically what's going to happen is this atom is going to act as an electrophile. So we've got the breaking of that bond here, an electron going here, because of that electron density. We've got the breaking of this bond here, an electron goes from the bond between hydrogen and oxygen to oxygen. And what's going to happen is that for now. Then we've broken those bonds, and now we're going to form a bond between that carbon. Oops. Go back. Broke the bonds here and here. We've now got our electrophile over here, and that carbon and the hydrogen form a bond together. And we've now got a positive charge on that carbon, so we form a carbocation at the top. A bond forms between one of the carbon atoms and the hydrogen atom, forming a carbocation. And now at the bottom, we've got a dihydrogen phosphate ion, which came from our phosphoric acid. But obviously we've lost a hydrogen, so it changes. So then we can have a water molecule come along, and our water molecule is going to act as a nucleophile. And one of the lone pairs in this molecule is going to attack the carbocation and bonds to the carbon. So our water comes along, acts as a nucleophile, attacks here, we get a bond forming here, but obviously we've still got that positive charge on our oxygen atom. Then we've still got that positive charge here. So one of our hydrogens on our, let me pause that here so we can see it better. So what's going to happen here is one of the hydrogens on the oxygen, so this one, for example, it could be either, is attacked by that lone pair on the oxygen in that H2PO4 ion, which was formed from the phosphoric acid catalyst. So that's going to be attacked here. So we've got movement of electrons from the oxygen to the hydrogen and breaking between that bond of the hydrogen and the oxygen. So that's as far as that's going to go. Oh, no, I did want that. So the hydrogen, so that's where we were. So then the hydrogen forms a bond with that ion, the H2PO4 ion, and it can regenerate the catalyst. And this also results in the oxygen and the hydrogen bond breaking here and leads to the creation of ethanol. So if we have a look here, that bond breaks. Ethanol is produced and phosphoric acid is regenerated. So oxidation, this is what we're going to look at now in alcohols. So we're going to look at types of alcohols, oxidation of alcohols, synthesis of oxidized alcohols, and esterification. So like all our other organic compounds that we've talked about, we can have primary, secondary, and tertiary alcohols, and that's all to do with how many R groups are attached. So, for example, primary alcohols have one R group attached, a carbon to which the OH group is attached. Secondary has two R groups. Tertiary has three R groups. Only quickly going through this because this is very similar. It's exactly the same, but obviously we'll just refer to alcohols when we say, oh, we've got primary alkenes and tertiary alkenes, for example. So when we come to oxidize them, it's different depending on if we're talking about primary, secondary, or tertiary alcohols. So this is where sort of differences come in. This is where the importance is, and where sort of that focus and attention really needs to come into it then. Right. So if we're going to oxidize our primary alcohols, first thing that we need to know, and this is really important, depending on if it's primary, secondary, or tertiary alcohols, they all oxidize to form a different product. So our primary alcohols, they always oxidize to form aldehydes. And it's important as well that you notice it's oxidized because it can change as well. So I'll explain that a bit more in a minute. So primary always oxidized to aldehydes, and that's using an oxidizing agent such as an aqueous solution of potassium dichromate. So when the symbol equation is written, our oxidizing agent is always represented by O. We do that because it's not always going to be acidified potassium dichromate. So in this example, we've got our general formula for any primary alcohol, oxidizing agent, and then showing our aldehyde is formed, and then water. Aldehydes we haven't come across before. You will have looked at them at GCSE. Aldehydes contain a carbonyl group. So that's a carbon double bond oxygen at the end of the carbon chain, and all their names end in al. So for example, propanal. So how do we synthesize these aldehydes then? We say we have to oxidize them, or how does this happen? What's going to happen is when we're preparing aldehydes by the reaction of a primary alcohol with acidified potassium dichromate, the aldehyde is distilled off and we collect, and that's to prevent further oxidation. So we heat the aldehyde at the, well, it's not the aldehyde, sorry. We heat the mixture of alcohol and dilute sulfuric acid and potassium dichromate. So we heat this. As it heats, it's going to condense. It's not going to condense, it's going to evaporate. It's going to go down the condensation tube. When it's going down here, we're obviously cooling it, so water comes in, water comes out, and what should come down is our aldehyde because they have different boiling points. So aldehyde has a lower boiling point than our alcohol. So aldehyde will come down, and then we distill it off and collect to prevent further oxidation because it can oxidate further. And this is the part I'm going to look at now. So if primary alcohols are reacted with an excess of oxidizing agent and then refluxed, they can be oxidized to aldehydes and then oxidized further to make carboxylic acids. So it's important to remember they still go to the aldehyde stage, but then it can go further to the carboxylic acids. So what would happen is this: we go from our alcohol, so our RCH2OH, plus our oxidizing agent, to our aldehyde, which is our RCHO, and our water. Then we carry on oxidizing further via reflux, and so then we're going to take our aldehyde, which is RCOH, and our oxidizing agent still, and then we're going to get RCOOH, which is our carboxylic acid. Carboxylic acids contain that carbon double bond oxygen at the end of the carbon chain with a hydroxyl group attached to the carbonyl carbon. So it would look like this. So carboxylic acids are named using the suffix oic acid, so carboxylic acid and propanoic acid. So how do we synthesize carboxylic acids? They must be prepared using a lot harsher conditions than those that we use to prepare aldehydes, and remember it's going to be refluxed. So what happens is our primary alcohol is mixed with an excess, really important because our oxidizing agent needs to be in excess of acidified potassium dichromate. It needs to be in excess, and that is to ensure that there is enough oxidizing agent present for the complete oxidation of the alcohol. So that's the first stage. Oh, and it's just telling us exactly the same thing. Interesting. So then what we're going to do is we're going to heat the reaction. We're going to heat it for a lot longer than we would when we were forming an aldehyde. And we do this so that reaction starts to be reflux. Reaction mixture is reflux. So I'm going to play that again. And this involves fitting our condenser and heating the mixture. So basically, as it heats, is it going to show us anything else? Yep. As it heats, it's going to start to evaporate and it's going to go up and down. And that's what we mean by reflux. So as the reaction mixture boils, our aldehyde is going to evaporate. It's then going to condense repeatedly. So it evaporates, condenses, and it drips back into the reaction mixture. And as it drips back into reaction mixture, it's going to then continue to be oxidized. So it's going to evaporate and condense and evaporate and condense. And what should happen is the color should change in our reaction mixture from orange to green. Now, the solution color changes due to change in oxidation state of the chromium ion. So it goes from +6 in dichromate ion to +3 in our final mixture. So that's really important to know. So this is our equation for complete oxidization of a primary alcohol to carboxylic acid. So we go, and we can see then we've got that changes of there. So secondary alcohols, we can oxidize secondary alcohols as well. If we oxidize those, they become ketones. We want to use an oxidation agent again, such as a solution of acidified potassium dichromate. Here is an example of one. So that's our ketone and general formula, which is R1CHOHR2. In the presence of our oxidizing agent, O in brackets, and then we're going to form our ketone. So that's our secondary alcohol. I don't know why I said ketone. So that's our secondary alcohol. That's our oxidizing agent. This is our ketone, which would be R1COR2, and then water. So ketones contain a carbonyl group, which is C double bond O, attached to any carbon in the chain except the terminal. So it's not going to be on the end. That is how it is different from an aldehyde. And we name them ending in -one, so propanone. Tertiary alcohols are resistant to oxidization due to the lack of hydrogen atoms on the carbon atom to which the hydroxyl group is attached, so it doesn't, they don't oxidize basically. So a quick look here, what is missing from each reaction, each oxidation reaction? So we've got our initial product missing, our type of alcohol, so we decided it's going to be a primary or a secondary alcohol. We're told that it's potassium dichromate, so that's our oxidizing agent, and it's going to form propanone, which is obviously a ketone, and water. So propanone, let's have a look at what our formula for propanone is going to be. Well, it's got that C double bond O in it that's not on a terminal chain. So that's going to be this one, which is going to go here. And then we've got this here. So we've got 1, 2, 3 carbons, which lets us know that it's propanol. And now I need to decide if it's propan 2-ol or propan 1-ol. Well, we know it's propan 2-ol because of where that OH is attached. So it's propan 2-ol. Here we've got butan-1-ol and potassium dichromate, and it's forming something with water. So if we have a look what it's forming, we've got CH3, CH2, COOH. So we've got our COOH, which is typical of carboxylic acids. And when we started with butan-1-ol, so that means it's going to form butanoic acid. So butan-1-ol, let's have a quick look at what that's going to be. So our butane's attached, our OH group's attached to our terminal carbon. Obviously, it's going to be this one. So we've got ethanol and potassium dichromate forming something and water. So let's have a look at what this something is. We've got CH3, CHO, and water. So we haven't got a carbon double bond oxygen. So it's not going to be an aldehyde. Let's have a quick look at what it could be. So what have we got? We've got ethanol. Let's have a look at how our ethanol would be formed in this situation. That here would obviously be a carboxylic acid, C double oxygen H. So it's going to be CH3, CH2OH for our ethanol. And now what are we forming? Are we forming an aldehyde? Are we forming a ketone? Or are we forming a carboxylic acid? Well, it can't be a ketone because we haven't even got a ketone option here. So we know it must be a primary one. So the decision then is, are we forming an aldehyde or are we forming a carboxylic acid? Well, we haven't got that carbon double oxygen hydrogen there, so it can't be ethanoic acid. It means it has to be ethanal. And finally, we're going to form propanoic acid in this one, which means that we have started with propanol. No. I'm trying to now decide if they're trying to do a tricky one here and actually put in the second part of that reflux part and actually go from an aldehyde then up to a carboxylic acid. We'll have a quick look. COCH3 going to be on an end one, so that can't be an aldehyde because that CO isn't on the end. That one is. So yeah. No, not propan 2 off. Propanol. So what they've done there is they've shown that second part of the oxidation. So that's the second part of the reflux that's going to happen. Why we're not working. Okay, so how do we distinguish between aldehydes and ketones? Very similar. They both have that carbon double bond oxygen in there. Aldehydes obviously have it on the terminal end, ketones not terminal. So how can we, so you could guess that they're going to have very similar properties. So to distinguish the difference between them works on the basis that the tests that distinguish between aldehydes and ketones work on the basis that aldehydes, but not ketones, have reducing properties, and therefore they can be oxidized to carboxylic acid. So basically the whole way we can test to see if they're one or the other is looking at if they can oxidize to carboxylic acids. So we can test using Tollens reagent, which is a silver mirror test. So you'll have come across this before. Sometimes we call it the ammoniacal silver nitrate. And we're just going to have a quick look at how we can use it to distinguish between aldehydes and ketones. So we have to make Tollens reagent up. So we make it by adding a small amount of aqueous sodium hydroxide solution. Oops. To our test tube, and in our test tube we're going to have silver nitrate already in there, and what this does is this forms a brown precipitate of silver oxide. So Tollens reagent is made and we add aqueous sodium hydroxide to aqueous silver nitrate, and this forms a brown precipitate of silver oxide. Aqueous ammonia is then added until the precipitate dissolves and starts to form a solution of the silver amine complex. So that's just making our Tollens, so we're still making a Tollens reagent. So here we go. So that's our ammonia being added, and it's going to keep being added until the precipitate dissolves and we form a solution of the silver amine complex. Once we've got that, the test substance is then added to the Tollens reagent, and the test tube is warmed in our hot water bath. So we get some of our test substance, whatever it is, we want to know if it's aldehyde or ketone, we're adding it to our Tollens, and then we're going to put that in a water bath. If an aldehyde is present, it's going to reduce the silver amine complex to metallic silver. And what this does is it forms a silver mirror precipitate on the inside of a tube, and that's if an aldehyde is present. So if an aldehyde is present, it's going to make that metallic silver mirror on our Tollens, and that's because it has reduced the silver amine complex. And this is what it should look like. So it goes to this really silvery, and we call it silver mirror because sort of it's almost like as if it was a mirror and you could see yourself reflected in it. There's another way. So we can use Tollens or we can use Fehling's. So Fehling's solution is a blue alkaline solution of copper 2 ions. So with Fehling's solution, we just add it to an empty test tube. We don't have to mess about making it. You don't need to know how to make it. We literally just get the Fehling's solution and add it to our test tube. Then we add our test substance to the Fehling's solution, and the test tube is then warmed in a hot water bath. And then finally, if an aldehyde is present, the solution is going to turn a brick red. That is because the aldehyde reduces the copper 2 ions to copper 1 ions, which forms a precipitate of copper 1 oxide, which turns the colour then from blue to red. Finally, in this little bit, we're just going to look at esterification of alcohol. So esters are another organic compound. So we've actually covered a lot with alcohols. We basically covered alcohols. We've then gone, oh yeah, here are aldehydes, here are ketones, here are carboxylic acids, oh yeah, and here are esters. So esterification involves refluxing a carboxylic acid and an alcohol with a concentrated sulfuric acid catalyst. So we've got our alcohol here, we've got our carboxylic acid here, and then we form an ester and water. So when we go to name esters, we will spend a lot of time looking at esters. We'll have a whole session looking at esters. The names of esters have two parts. The first is based on the carbon chain of the alcohol, and the second is based on the carbon chain of the carboxylic acid, because they are basically the joining of a carboxylic acid and an alcohol. So this part of the name would come from the alcohol, and this part of the name would come from the carboxylic acid. So for example, if we reacted methanol and ethanoic acid together, we would form methyl ethanoate. But we will look at that in a bit more detail another time. So really quickly, if we're looking at what oxidizes what reaction conditions are required to produce butanone? So if you ask this question, the important thing to look at is butanone. What is butanone? It ends O-N-E, which means it's a ketone. If it is a ketone, that means it needs to have been a secondary alcohol that has been oxidized. So straight away, it can't be butanol because that's been refluxed. Butan-1-ol has been distilled with an aqueous solution of acidified potassium dichromate. Butan-2-ol has been heated with an aqueous solution of acidified potassium dichromate. Well, what's the difference between butan-1-ol and butan-2-ol? Well, butan-1-ol is not going to be or if we words, we now need to look at whether it's going to be a primary, secondary, or tertiary alcohol. Butan-1-ol will be primary, so it's going to be butan-2-ol because that will be secondary. So this one, what reaction conditions required to produce ethanoic acid? Here we go. Ethanoic acid is going to be a carboxylic acid. We're looking at it from an alcohol perspective, which we're talking about ethanol here. It needs to be refluxed. What's it going to be refluxed in? It's going to be refluxed with excess potassium dichromate. What reaction conditions are required to produce propanone ketone? Let's have a quick look then. We're not refluxing anything. We're not distilling anything. We're heating, and obviously it needs to be a secondary alcohol as well. Propan-2-ol is a secondary alcohol. So it's that one. What reaction conditions are required to produce propanal? Propanal is an aldehyde, so that needs a primary alcohol being oxidized. Propan-2-ol is a secondary, so it can't be that. Propan-1-ol refluxed would give us carboxylic acid. So it's going to be propan-1-ol distilled with an aqueous solution of acidified potassium dichromate. Finally, what reaction conditions are required to produce hexanoic acid? Hexan-1-ol refluxed with excess acidified potassium dichromate. Hexan-3-ol or hexanone. Well, it's not going to be hexanone because that's a ketone. Can't be hexan-3-ol because that would not be a primary alcohol, so it's going to be hexan-1-ol. So, yeah, let's get the last little bit of alcohols done, and then we'll go through some exam questions based on alcohols. If it will open. Other reactions of alcohols. We just need to know a couple more reactions with alcohols. So a little bit more about making alcohols from aldehydes and ketones. So we can do the opposite. We can make aldehydes and ketones from alcohols, and we can actually do the reverse, and we can make alcohols from aldehydes and ketones. Also look at how ethane is made from alcohol. We've already spoken about how we can make ethanol from ethane. We're now looking at the opposite. Combustion of alcohols, sodium reacts with ethanol, and forming halogenoalkanes from alcohols. So aldehydes and ketones can be reduced by a reducing agent such as sodium borohydride to form alcohols. Makes sense. We can make aldehydes and ketones by oxidizing alcohols. So if we reduce aldehydes and ketones, we can form alcohols. When we write the symbol equation, our reducing agent is going to be represented by H, oxidizing represented by that square brackets O, reducing agent square brackets H. So aldehydes are reduced to primary alcohols. It makes sense. Primary alcohols are oxidized to aldehydes. So it's just basically the reverse. So we've got our aldehyde here, reducing agent, primary alcohol. And as you can probably work out from that, ketones are then reduced to secondary alcohols. So ketone, reducing agent, secondary alcohol. So how is ethene made from ethanol? Probably guess, as you can see, this is a reversible reaction. This is going to be exactly the same as when we talked about it before, but the opposite way around. So alkenes can be made from a dehydration of ethanol, which makes sense because we made ethanol by the hydration of alkenes. So it's a reverse reaction of the hydration of ethene. So basically it's a dehydration and an elimination reaction due to our removal of water. And concentrated sulfuric acid is going to be used as our catalyst in this situation. It's going to take place at a temperature of 450 Kelvin, exactly the same as before. So what happens? Our sulfuric acid is going to be a polar molecule. What happens here is polar molecule. So the lone pair on the oxygen of the alcohol attacks the slight positive charge on one of its hydrogens, and the hydrogen is now going to act as an electrophile, as you can see here. So sulfuric acid comes along. You see that movement of the electrons here to here. This bond breaks between the oxygen and the hydrogen. So what then happens is a bond forms between the hydrogen from the sulfuric acid and the oxygen on the alcohol, and that forms protonated ethanol. So we say the ethanol's now been protonated. Our sulfuric acid has lost a hydrogen and so becomes hydrogen sulfate ion. Carbon-oxygen bond on our protanoate breaks and we can form a carbocation. So the carbon-oxygen bond on that protonated ethanol is broken and we form a carbocation and water. One of the hydrogens on the non-positively charged carbon of a carbocation is attacked by the lone pair on the oxygen in our HSO4 negative ion. And then finally, that hydrogen forms a bond with the ion, regenerates the catalyst, and this also results in a second carbon-carbon bond forming, leading to that creation of ethene. So in the lab, dehydration of ethanol can be achieved by passing ethanol over a hot aluminium oxide catalyst. So we've got ceramic wool soaked in ethanol here and our aluminium oxide in our test tube. So as we heat it, the ethanol is going to start to evaporate. It's going to pass over the aluminium oxide catalyst. When that happens, it's going to release that ethane gas, and that's going to go down the tube and it's going to be displaced in here as ethene gas up here. Combustion. Alcohols are able to undergo complete combustion and they form carbon dioxide and water. Denatured alcohol is ethanol that has been made toxic and undrinkable by the addition of other chemical additives. So a traditional additive was methanol, which formed methylated spirits, which is 90% ethanol and 10% methanol. Denatured alcohol is really useful for portable fuel, for things like camping stoves, as unlike LPG, it doesn't need to be transported in heavy specialized containers, and we can also use it as a solvent. So how does sodium react with ethanol? So a bit of another random information about ethanol now. So if we put a piece of sodium into a trough filled with ethanol, what's going to happen? Well, it sinks to the bottom and it starts to fizz. What's going to happen is that's going to create gas. We can collect that gas in a tube. So we can put an upturned test tube in there and collect that gas. And the rate of gas production is slower than when sodium reacts with water. So the ethanol reacts with the sodium to produce hydrogen gas and sodium ethoxide. And the gas can then be tested by holding a lighted splint to the mouth of the test tube. And the last little bit, we can form halogenoalkanes from alcohols. So primary, secondary, and tertiary alcohols all react with phosphorus chloride to form a chloroalkane. So if we add phosphorus chloride to an alcohol at room temperature, it produces white hydrochloric fumes as well as a chloroalkane. And this reaction can be used as a test for alcohols, as well as a method of producing halogenoalkanes. What I'm just going to do now is pause this. Okay, so what we're going to have a quick look at now is a few exam questions based on alcohols. So our first one here, in the UK industrial ethanol is now produced by direct hydration of ethene. The process has largely replaced the fermentation method. Which is a likely reason for this change of method? So why might they have done it? So the direct hydration route produces ethanol by slower reaction. While if it does it slower, that would make no sense. We wouldn't want to do it that way. So even if we didn't know the answer, we could say, well, it's not going to be that one. I'm just going to double check that we can see this screen still. Yeah. The direct hydration route does not use a catalyst. It does use a catalyst, so it's not that one. The direct hydration route employs milder conditions. It doesn't, it needs stronger conditions, but the direct hydration route produces pure ethanol, and that's true. That's why we use that. Oops, didn't want to do that. So let's have a quick look at this experiment. A group of students want to produce a biofuel to power the central heating system in their school. They collect scraps of fruit and veg from the kitchens and ferment them with yeast in the absence of air in order to produce ethanol. The aqueous mixture was filtered to remove the remaining solids, and the students set up the apparatus shown in the diagram below and place the aqueous mixture in a round bottom flask. Describe how the students would use the apparatus to collect a sample of ethanol, including your answer for functions of the parts of the apparatus labelled A, B, and C. So let's have a quick look at A, B, and C. So let's just talk this through. So what's going to happen? What are we going to do? So what's the question? Again, describe how the students would use this apparatus to collect a sample of ethanol. Okay. So they want to produce a biofuel to power the central heating system. They collect scraps, ferment them with yeast in the absence of air to produce ethanol. Okay. First thing they're going to do is we've obviously got this condensation tube over at C. Before we do anything else, first thing that you're going to want to do, and I'm going to actually sort of talk it through here and write things on here. So our first stage, the first thing that we're going to ever want to do on anything like this that has a condensation tube involved is actually turn on the water. If we start heating anything, before we've got that water turned on, going through a condensation tube, it's not going to work. It's not going to be effective. So we're going to turn on the water for our first part. And that's going to be for our condensation tube. So that's going to be for C. So obviously you'd want to write a full sentence there. You're going to want to put turn on the water for the condensation tube, which is C. We're going to heat the flask with a Bunsen burner. So that's going to be part 2. So we're going to heat flask with Bunsen burner. Heat flask, we don't have the flask labeled or anything, that's fine. With Bunsen. So obviously we need to turn on water first. Then we're going to heat this flask with the Bunsen burner. And what this is going to do is this is going to cause our water and ethanol vapors to be produced here. So therefore H2O and ethanol vapors are produced. That's stage 1. Let's look at stage 2 then. So the vapors are going to go up A. So this is where we're going to say what A is. So 2, and that is obviously our fractioning column. So vapors pass up the fractioning column. Column, capital an N, and water and ethanol are going to be separated in the column. So water and ethanol are separated here, water and ethanol are separated here. And water is going to condense back into the flask in column A. So water condenses back into the flask. B, obviously, is a thermometer. So let's have a quick look at that. We want to include that in. That's going to come in stage 3. We're going to want to observe the thermometer at B. And that's to make sure the temperature is below the boiling point of ethanol. If we go above the boiling point of ethanol, we're going to get in a mess. So stage 3, we want to observe by, I'm just going to put by using B, so I don't have to write thermometer, but you know that's obviously thermometer. By using B, that boiling point. That's so that we can fractionally distill this. Make sure that the boiling point, or make sure that the temperature, better would make sense, temp, remains at the boiling point of ethanol. Therefore, only ethanol vapor passes into the condenser. Null, even. Our condenser obviously is C, so then we've included C again. And the condenser cools the vapors, and this cools the vapors. So that would be I can't remember how many mark question is this. Let's have a quick look. Is a 6-mark question. So that's all the indicative information that we need. So they're all the key points that we need to get those marks. So basically the minimum is 1 to 2 marks you can get and these sorts of questions. So we've then leveled them. So you need the information in there, but they need to be written in logical process. So to get those 5 to 6 marks, to get those top marks, you need all that information there that I've just talked through. But basically all those stages need to be covered, and the evaporation of each stage is generally correct and completely and complete. So you're saying, well, this is going to evaporate in that. Your answer needs to communicate the whole process completely coherently, and there needs to be logical progression through the distillation apparatus. So basically turning on the water, heating the flask of the Bunsen burner, and water and ethanol vapors are going to be produced. Then it goes up here. So we're basically following the system down. So it needs to be logical in that process as well. And those first 2 stages in point 1 had to be in the correct order. Everything else could be logical. So to get 5 or 6 marks, you must say this one first, turn on the water, then heat the flask. If you miss one of them out or put them in the wrong order, you cannot get more than 4 marks. So that's really important to know. I'm just going to skip this maths question for a minute because I just want to focus on. No, actually, I'm going to do this one. I changed my mind because then that finishes off this question. Oops. So the students collected 20 cubic centimeters sample of liquid and they weighed it, and the mass of the sample was 16 grams. The density of ethanol is 0.79 grams, and that of water is 1 gram per cubic centimeter. So we're going to use this data to calculate the mass of ethanol in the sample collected. And you have to assume that the volume of the sample is equal to the sum of the volumes of water and ethanol. So from that information, we can say our volume of our sample equals our volume of ethanol So volume of ethanol plus our volume of water. So students collected 20 kilometers, 20 cubic centimeters sample of liquid and weighed it. So that's obviously going to be our ethanol and our water. So our mass, so that is 20 cubic centimeters. So the mass of sample is 16 grams. So our mass is going to be mass, and we're going to divide that by obviously our volume here, which is 0.79 plus our 16, divided that by 1. So then that will give us 1.266. 20, oops, 20 minus 16, because we've got our 16 there. I'm just rearranging at the moment. So therefore we should get 0.266 our mass would be 15 grams, because we're just taking that one off basically because of our 1 gram there. So yeah, I don't want to do that right now. Complicated questions. Here we go. Just want to do this one really quickly. Question 5. So glucose is an organic molecule. Glucose can exist in different forms in aqueous solution. In aqueous solution, some glucose molecules have the following structure. It wants you to deduce the empirical formula of glucose. No, I don't want to look at glucose at the minute. Not what I want. So well, we'll leave that there for now.